Hello students, welcome to this lecture. So the switching resistance by definition, it is nothing but an average of all the DC resistance for the voltage range we are interested in, right? So this is nothing but an average of all the voltage, the average, the DC resistance. So VDS divided by IDS is nothing but a DC resistance. So DC resistance means for a given current IDS value and for a probed VDS value, what is that particular resistance? So this is nothing but a DC resistance picked at every point in the voltage, right? And then the average of that, whatever the range we are interested in. So if it is 0 to VDD, this is the range 0 to VDD. We want the 1 by VDD which will give us the average. So it is basically a voltage weighted DC resistance and the average of that. So an average of the voltage weighted DC resistance is nothing but the switching resistance. So this is what we will use it for our equivalent RC model for any kind of a digital circuits. All right. So let me use one more example. So what it means is, so if I have a resistance axis, a resistance profile with respect to the VDS value of the transistor. So in this particular sense, I'm going to use the NMOS transistors and then have a particular point. So from 0 to VDD, we know that when the VDD, when the voltage is VDD, the NMOS transistor is in saturation. We will have a very large current, and then we will have a very small resistance. So similarly, as for an inverter circuit, as the output node voltage drops, the VDS values keeps dropping. The VDS values keeps dropping, and somewhere at 0.7, we will get it will change to the linear region, and then till it is 0. So if you are actually looking for a resistive, the switching resistance value for a range of 0 to VDD or VDD to 0, so we might actually end up seeing something like this, the resistance values. So I'm just drawing an example. I'm not sure whether this is a real profile. And what this integration of 0 to VDD or VDD to 0 does is it takes all these resistance values, all right? It takes all these resistance values across this particular VDD value. So it is basically drawing, integration is nothing but an area. So it is basically taking an area of this and then does the 1 by VDD, this particular range of 1 by VDD, so that I will actually get some kind of an average value. So this becomes a switching resistance. So hope you understood this particular aspect of the switching resistance, which we are going to incorporate into our RC equivalent model for the transistor based circuits. Right. So yeah, so this is what the definition says. And if we are interested in the propagation delay falling or rising, this particular range will not be 0 to VDD. So this particular range of 0 to VDD, it will not be like that. It will be either VDD to VDD by 2 or 0 to VDD by 2, something like that. Right. So wherein the switching resistance is for 0 to VDD by 2 or VDD to VDD by 2. All right, so that's what I have written here. So for the propagation delay falling, the range is actually VDD to VDD by 2. So that's what, the switching resistance from VDD to VDD by 2 and the DC resistance calculation, right? So dVds is likely to decrease because it is ranging from VDD to VDD by 2. So this is going to be decreasing. So that's why, for every resistance, the resistance is a scalar quantity, and we will have a positive value of a resistance. We will never have a negative value of a resistance. And that's why a negative sign is here to accommodate for the decreasing change in this integral expression. Right. So this is what the expression for finding the switching resistance. The switching resistance for evaluating the propagation delay, which is from the output node voltage starts from VDD to VDD by 2. So this is what the expression will be. For calculating, finding the equivalent switching resistance for the propagation delay rising, it will be starting from 0. The integral will start from 0 to VDD by 2. So there we will not have this negative sign. There we will not have this particular negative sign. Hope this is clear. The definition of the switching resistance and the expression for the switching resistance is clear. So let's try to calculate the switching resistance for the long channel current model, and then we will try to calculate it for the short channel current model. Right, so VDD by 2 here, for the range of VDD to VDD by 2 for the propagation delay falling. So I'm trying to find the switching resistance for the propagation delay falling. So that means the output range is actually nothing but VDD to VDD by 2. So in this, I will have 1 by VDD by 2. So the 2 goes here and there is a minus sign. And then this particular range is now changed from VDD to VDD minus VT, and then VDD minus VD to VDD by 2, because here the current, when we take the VDS by IDS, right, in our expression for the switching resistance, the current in this particular range of the voltage, when it is within the VDD to VDD minus VT, it will be the saturation region. And when it is VDD minus VT to VDD by 2, the last time also we had seen from 1 volts to 0.7 volts, it will be in saturation region. And then from 0.7 volts to 0.5 volts, it will be in the linear region. So we will have a separate current expressions. So that's why we'll have to separate the integrals. Separating the integrals, we will get, we can easily write the expressions here, beta by 2 into VDD minus VT the whole square. And then the linear region, the current will be beta multiplied by VDD minus VT minus VDS by 2 into VDS. So this VDS and this VDS gets cancelled. Here, this is all constant. The denominator parameter is all constant. We can easily take it out. So the integral for this VDS with respect to dVDS will be nothing but VDS square by 2. And here, there is a term of VDS in the denominator. So the integral of this will be nothing but the log. Moving ahead. So the R switching will, if I further solve this. So, this particular slide just shows, the further steps on finding out the R switching value. So finally, the R switching value turns out to be this 3.0868 divided by beta. This beta is for the W of 1 micron, and 1 micron. So that is what I'll get, 5.26 into 10 raised to minus 3. Eventually I'll get 0.586 kilo ohms, right, for a width of 1 micron in the long channel. So this is my long channel switching resistance. So just, if just going back a slide so that, I hope that I have not missed anything. So this is this particular beta value, beta value and all those things. This is nothing but for a W of 1 micron. Right, I'm keeping this 1 micron constant because, from the transistors, in the transistors, in NMOS transistors, we had taken that current equation. And then from the current equation, we had produced the voltage profile. And from the voltage profile, we had calculated the propagation delay falling. That propagation delay falling was for the width of 1 micron. So keeping that width of 1 micron, we want to benchmark whether the switching resistance, makes some appropriate sense. So in this particular slide, what we had done is we had calculated the 0.586 kilo ohms. And if I use the R switching long channel resistance with that of a capacitive load of 20 femtofarads, the propagation delay, whatever the expression we had seen, R multiplied by C will be my propagation delay multiplied by 0.693 will give me 8.12 picoseconds, right, which is very, very close to my long channel transistor current based propagation delay falling was somewhere around 7.79 or 72 picoseconds, right? So if I use the switching resistance of 0.586 kilo ohms and treat it like an RC circuit, my propagation delay falling, right, for a step input is coming close to the value, it is coming close to the value of 7.72 picoseconds. So no need to take the transistor current equation, voltage profile, and then the propagation delay falling, and then finding out the value of 7.72. Rather, if I can find out, if I have a switching resistance value, use that of 0.586 multiplied by the capacitance multiplied by log of 2 or 0.693, I will get this particular propagation delay falling value. Right? And note that if the betas are same for the PMOS and NMOS, the propagation delay falling and rising will be equal if the betas are same. So hope that is clear. Moving ahead, what is the switching resistance? If I use the short channel current model. Now remember that the propagation delay falling using the short channel current model was somewhere around 10.86 or 10.79 picoseconds. So what we need is to benchmark this. We will also calculate the switching resistance using the short channel current model, and try to see that the R switching of the short channel multiplied by the C value, and multiplied by 0.693, whether it comes closer to that particular value. Right, the short channel, I'll write the same expression of the switching resistance. Here it is VDD to VDD by 2, and then VDS by divided by IDS. The current for the short channel here, it will be a single, because the NMOS transistor will be in saturation region till it reaches 0.411 volts. So from 1 volts to 0.411 volts for the falling output, the NMOS in the short channel will be in saturation region. Right, so that's why for the NMOS, the VDS saturation value is 0.41. That's what we had arrived. Hence, for the range of VDD to VDD by 2, we know that the IDS value which we have to take, it is nothing but IDS saturation. Moving ahead, IDS saturation for the short channel is nothing but WC oxide velocity saturation into VGS minus VT minus of VDS saturation. The VDS saturation is anyways fixed, which is 0.41 and then 0.7. So it turns out to be 2.29 WC oxide velocity saturation. This, if I take this into the current expression, and then VDS by IDS into dVDS. So all these parameters are the constant value. So I can easily take it out. So what remains inside the integral is this VDS. So the solution of that integral will be VDS squared divided by 2. So that's what I've done here. Okay, so VDS square divided by 2, and then finally what we will see is 0.5 square minus of 1 square. So 0.5 square minus of 1 square, so 0.75, which I've written it as 3 by 4. And so eventually I'll get 786 ohms. Right, so if I solve that particular integral, I'll likely to find 786.4. Whereas for the R switching calculated or estimated R switching using the long channel current, we got somewhere around 0.586, right, kilo ohms or 586 ohms. Intuitively, it says that the switching resistance estimated for the short channel current model is more, and which is in a way it is correct, because the current for the short channel model will be less than that of the current that has been estimated from the long channel current. And if the current is less, the resistance is likely to be more. So that's what we have got, 786.4 ohms. And if I use this particular switching resistance of the short channel, multiply with that of the load capacitance of 20 femtofarads, and then 0.693, assuming that there is a step input, I will get somewhere around 10.89 picoseconds. So sorry for that, this slide I missed 0.693. So if I multiply by 0.693, I'll get 10.89 picoseconds, right? Whereas we had calculated using the transistor short channel current and then evaluating the voltage, output voltage expression, the linearly decreasing profile, and then putting the 0.5 volts, we had identified the TPDF using the transistor current equation as 10 point some value, 10.79 or something like that. And here we are reaching very close to 10.89 picoseconds, which is very close to what we had earlier calculated. So if I somehow find out the R switching resistance and multiply by that of the capacitive load, and of course multiply by log of 2 if it is a step input, then I'll likely to get the propagation delay falling for the transistor circuit, for the digital transistor circuit. Right, hope this is clear. So just to summarize, the short channel, the short channel model, the switching resistance for the NMOS transistor, and all this while we had taken the switching resistance, we had considered the switching resistance of an NMOS transistor. Because when we apply the input, step input of 1 volts, the NMOS is on, the NMOS is operating, the NMOS is driving the capacitance, the output load capacitance. It is driving the discharging of the output load capacitance to 0 volts. The PMOS is completely off. So the operating transistor is actually NMOS, and we had used the switching resistance in the switching resistance for the NMOS transistor, we had used the current of the NMOS. So nowhere we had actually used the current of the PMOS. So the short channel model based switching resistance for the NMOS for the width of 1 micron was turning around 786.4 ohms. If I lower the width, so the width of the transistor, NMOS transistor, if it is decreased from 1 micron to 100 nanometers, so it is 10 times decrease. So my resistance is likely to increase by 10 times, right? And then the answer is very, very simple. If I go back to that current equation, so go back to the slide number 12, I will notice that this W, this W was of, now this particular W is actually going here, right, into the denominator expression. So this is the W, right? So if this W is 1 micron, right, that has been changed to 100 nanometers. So effectively, so from 1 micron to 100 nanometers, so effectively this whole switching resistance is likely to be multiplied by 10, because W is anyways a constant which will come outside the integral. So moving back, so if it is decreased by 10 times, so the resistance is going to increase by 10 times. And intuitively, if I look into the cross-sectional transistors, what we are saying is, so if this is the length and this is my gate side, this particular width is increasing. So the cross-sectional area, so the channel cross-section area, so this being, if I consider this to be the terminals A and B, right? So the RAB value and its cross-sectional area, so which I can consider it to be an RAB, which will be nothing but, if I can rewrite into a simple expression. So this particular area, which is nothing but, W by the depth of the channel, this length is nothing but the channel length, right? So this is this channel length. Area is nothing but the width, and N2 multiplied by, so this is nothing but the width multiplied by the channel depth, right? So which we are not considering. What we are saying is this: if this W decreases, intuitively this RAB increases, and that's what we are getting. The switching resistance is increasing. So it is increasing by 10 times if the width has decreased by 10 times. In the long channel, if I use, we had calculated the long channel switching resistance for the NMOS transistors for 1 micron, which was around 586 ohms. So if I use a width of 100 nanometers, again, the resistance is going to increase by 10 times. Hope this is clear. Moving forward, just to summarize, R NMOS, if I consider it to be an R long channel or whatever, the short channel. So here I'm taking the long channel as R, which is nothing but for 100 nanometers. So it is nothing but 5.86. So instead of 5.86 kilo ohms, so if I actually say that this is, an R value, just a constant R, the PMOS long channel for the same dimensions, right, it will be 2R. And then the reason is very, very simple. The beta, if I'm using the same width, the beta of the PMOS, in this case, the beta of PMOS will be half that of the beta of NMOS. So if I want the betas to be same, I have to make the width to be twice, width of the PMOS to be twice that of the width of the NMOS. Because the beta is less, my current will be actually be less, and thereby the current will be actually be less by half for the PMOS, and thereby my switching resistance is going to be more, so be exactly twice that of the NMOS. Right. So what I mean by a resistance R here for an NMOS transistor is nothing but the lowest dimension NMOS transistor is going to give me a resistance of R, which is nothing but 5.86 kilo ohms. Right? Why do I say the lowest transistor or the lowest dimensioned NMOS transistor? Because it is a unit NMOS, so 100 nanometer is the lowest width I can go. 50 nanometers is the lowest channel I can get in a 65 nanometer technology node. So that I will get a switching resistance for the NMOS transistor as R. Similarly, for a unit PMOS transistor, if I have the lowest PMOS transistor, which is 100 nanometers and 50 nanometers of the channel length, I will get a resistance of 2R, where R is nothing but the unit NMOS resistance. So I'm having the PMOS resistance, switching resistance, and then the NMOS switching resistance, trying to do a relative comparison. Moving ahead, so what we need is basically a capacitive load also. So if I can also express the load capacitance in terms of a constant C, right, it will be much easier for me to understand if the transistor width increases or decreases. If it scales, what should be the capacitive scaling effect. So the gate capacitance here, so if I write the gate capacitance, it is nothing but epsilon naught K by T oxide into A. So the capacitance is nothing but epsilon naught, the dielectric constant A, and then the thickness T oxide. Right, where A is nothing but W multiplied by L, so that's what I have written here. So it is directly proportional to the W. So if I consider a unit NMOS unit NMOS transistor, my W is actually 100 nanometers. If my W is 100 nanometers, the CG value turns out to be 0.16 femtofarads for an L of 50 nanometers, W of 100 nanometers for a 65 nanometer technology node. For a W of 1 micron, which is 1000 nanometers, the W increases, the area increases, rather the W increases, so the CG value will also increase. So the CG, I can write it in terms of KW. If my dimensions, if the width increases, it scales by K times, where W is the width of the unit NMOS, that means 100 nanometers. If it scales by K times, my capacitance, the gate capacitance, also scales by K times. So CG is also 10C if W is increased or scales by 100 or 10 times. Diffusion capacitance also has a value very, very close to that of the gate capacitance. So the diffusion capacitance, if the gate capacitance is somewhere around 0.16 femtofarad, the diffusion capacitance is also somewhere very, very close. So it turns out to be 0.14 or 0.13 femtofarads. So what we will say is that for a unit NMOS, the diffusion capacitance also will consider it very, very close to the C value, the gate capacitance. So to make our overall, the RC equivalent circuit very, very simple to express. So what we are doing is we are expressing the gate capacitance in terms of a constant variable C, diffusion capacitance also in terms of the constant variable C. So the diffusion capacitance, it is also directly proportional to the W. So if you see the diffusion capacitances or the depletion capacitances, if the W increases, the area of the depletion capacitance also increases. Right? So the diffusion capacitance for an NMOS, if it is K times more, I will get the diffusion capacitance also to be K times multiplied by C, where C is nothing but the unit NMOS transistors gate capacitance or the diffusion capacitance value. So I can see diffusion capacitance of the PMOS is also, if it is increases by K times, I will also get, for the same dimensions, the PMOS capacitance remains the same as that of the NMOS capacitances, right? Only the resistance for the same dimensions of the PMOS as that of the NMOS, the resistance is, the switching resistance is half that of, and the switching resistance is twice that of the NMOS switching resistance, right? So just to summarize, for the kW width, NMOS resistance, switching resistance, if it increases, will be nothing but the unit resistance, that is for 100 nanometers divided by K. For the PMOS, for the W, W is nothing but 100 nanometers. For the unit PMOS transistor, it is nothing but 2R. If it is scaled by K times, if the width is scaled by K times, it will be 2R by K. Capacitance, on the other hand, for both PMOS and NMOS, if it is scaled by K times, the width of the transistor, if it is scaled by k times, the capacitance, the gate capacitance is nothing but k into C. PMOS also we will have the gate capacitance k into C. Diffusion capacitance is also k into C, and the diffusion capacitance of the PMOS is also k into C. So just to summarize, the switching resistance is different for PMOS and NMOS, whereas the capacitance remains the same for both of them if it is if the width is scaled by k times. Right. So overall, in this particular lecture, what we had seen is how to evaluate the switching resistance for an NMOS using the short channel or the long channel current model. And then we also validated, if we use that particular switching resistance and then multiply it by the capacitance, load capacitance, and then we get the values very, very close to what we had estimated from the transistor current equations. Right. And then finally, if I want to express for a different width dimensions of the transistors, we can express that in terms of R by K value as a switching resistance, or 2R by K value for the PMOS switching resistance. And the diffusion capacitance and the gate capacitance can be expressed as K multiplied by C.